Hello everyone, welcome to IIT-JAM Chemistry tutorial number 35, and this is lecture number 13 of the Physical Chemistry chapter Liquid State. Effect of temperature on viscosity of liquids is the subtopic of this lecture. Before starting this main subtopic, we have to have an idea about viscosity activation energy. You know about the terms laminar flow or turbulent flow. In case of a laminar flow, a molecule pushes back its neighboring molecule in order to go ahead. Now this molecule, in order to do this, has to overcome an energy barrier. So a molecule pushes back its neighboring molecule and goes ahead, and next the molecule has to overcome an energy barrier to do this, and this energy barrier is known as the viscosity activation energy, and it is denoted as capital letter E in the suffix small letter VIS, that is EVIS. Now coming to the main subtopic, temperature dependence of viscosity of liquids. You must have to mention this term liquid because temperature dependence of viscosity of gases is completely a different topic. Now if N is the number of moles of such energized molecules, that means the molecules which have energy greater than this activation energy or equal to this activation energy, they will only allow the liquid to flow. This number of molecules in the unit number of moles according to the Boltzmann distribution law can be related to the exponential factor. N is directly proportional to exponential minus EVs by RT. Here I have written here number of moles. In some textbooks it is written number of molecules, but do not get confused with these two, because if you write number of molecules, then you have to write here molecular activation energy epsilon vis. And here in place of R you have to mention the Boltzmann constant K. But since I have written it in the mole unit, then I have written here the molar viscosity activation energy, whereas in place of K I have written here the universal gas constant R. So you have to be very much alert about these two things. Now as much as this energized number of molecules would increase, the flow would be more easier, or the fluidity of the liquid would increase. That is, this N in turn is directly proportional to fluidity, and it is inversely proportional to viscosity, because viscosity and fluidity are reciprocal of each other. So fluidity is directly proportional to this N, whereas viscosity coefficient is inversely proportional to this 1 by N, because fluidity and viscosity are reciprocal of each other. So in place of N we can put this phi or fluidity, and if you put eta here, then only just change this negative sign into positive sign. So we can make two different relations, proportionality relations. One is fluidity directly proportional to exponential minus EVs by RT, and another one is viscosity coefficient is directly proportional to exponential plus EVs by RT. Now if this relationship is carried forwarded in the next slide, then we have to convert this into an equation just by putting a proportionality constant, and this proportionality constant is capital letter A. Thus we get equation number 18. So from here we can get the dependence of viscosity of liquids on temperature, and graphically it can be shown by this if eta is plotted against T. Now if you take natural log of equation 18 in both sides, then this relationship is obtained. Natural log of eta equals to natural log of A plus EVs by RT. If you take 10 base log, then just divide this here, just put 2.303 in the denominator, then it would become 10 base log. So in place of this you can also write log eta equals to EVs by 2.303 RT plus log A. Now EVs is a constant, R is also a constant, and 2.303 is a number. So in place of this you can put here small letter a, which is yet another constant. A is a constant, log A is also yet another constant. So in place of this you can put another constant, you can write it like B. So we get equation number 19. So that A and B are constants. A has the value EVs by 2.303 R and B has the value log capital letter A. So the graphical plot of equation number 19, if log eta is plotted against 1 by t, then you will get a straight line with intercept b and slope a. So that's all about temperature dependence of viscosity of liquids. So what conclusion we can draw from this? We can conclude that viscosity of a liquid decreases with increasing temperature. Viscosity activation energy can be determined from graphical plot of log eta against 1 by t. Here look this graphical plot again here. From the slope you can easily get the value. Slope is a, and a, small letter is nothing but E vis by 2.303 r. So from that you can easily get the value of E vis. And finally, what about constant a? If temperature is infinity, then 1 by t is 0. So if you extrapolate this straight line, it will merge here, and this becomes log a, log eta becomes log a. That is, a is actually the viscosity coefficient at infinite temperature. Okay. Now move on to the question. This question came in IIT-JAM in 2023, and the question is the diagram that best describes the variation of viscosity of water with temperature at 1 atm is, you are given 4 options. So which one is correct? Just move on to the previous slide. This one was the relationship, isn't it? This one was the relationship according to this equation number 18. So we have the answer. The correct option should be definitely option A, isn't it? So the mathematical expression of viscosity coefficient of a liquid as a function of temperature is eta equals to some constant into exponential E vis by RT, which is actually equation number 18. Therefore eta decreases with increasing temperature. That is, option A is the correct answer. So that's all about this subtopic. Thank you. Have a nice day.